experiment 3. So we'll talk, or sorry, experiment 2. I'm jumping ahead. Experiment 2 this week. So we're going to be talking about that today in lab lecture. We're going to also be collecting melting point ranges for experiment 1 and what time is left before or after you do experiment 2. So some of you have been coming to Open Lab, which is a really good idea because we only have 13 melt temps. So at one time, 13 people can be collecting melting point ranges, but not everybody all at once. So it is helpful to get ahead on that as well. We also will have our second quiz this week, okay? Next week, you are supposed to come to lab, so we're giving you the time to collect melting point ranges. Next week, you need to come to lab with the identification of your unknowns for experiment 1. So that means the melting points need to be done, and you need to know what, or at least propose what you think you have, okay? So know enough information to propose the unknown identification. Then we will be doing experiment 3, part 1. But for that entire experiment, you need to have the pre-lab ready to go next week for experiment 3. Okay, so experiment 2, there is not a pre-lab, and I kind of talked about that a little bit last week. I'll tell you today what you're going to do instead of a pre-lab, but experiment 3, we're going back to having a pre-lab again. So make sure you have that for the entire experiment before you come to lab, not just for part 1, all right? And read over experiment 3. In there, you're going to find information that's going to help you with putting that pre-lab together. Okay, and we'll talk more about it next week in lab lecture. So today with experiment 2, we're going to be looking at different types of models. And in general, when we're talking about looking at compounds, not just organic compounds, but looking at atoms or compounds or things in chemistry in general, there's 2 different things that we can use. We can use either physical models or we can use computer models, okay? And so, first of all, why are we going to use models? What is the reason to do that? One reason is, I mean, we're talking about all these different compounds, but can you actually see one physical compound, like in your white solids? Can you physically see one of the compounds so you know automatically what it is? We can't see that, right? So we kind of need a way to conceptually visualize what we're looking at. So for visualizing molecules and seeing molecules in 3D, this is one way to do it. Or seeing what molecules are proposed to look like in 3D. For understanding conformations and energy barriers. So you've been talking about some of this in organic lecture. And so one of the things that you've been talking about is Newman projections, and that's a type of model that you use to understand what is going on with different compounds. And so kind of as a review, we're going to look at a couple examples so we know that we're all on the same page with that, because we'll need that this week. So if we draw a Newman projection for ethane that looks like this, what conformation is that of ethane? Anti or staggered, right? Is it an energy minima or energy maximum? Minimum. It's a minimum, right? Okay, how about this guy? So, you know, the exact opposite here. So which one is this one? The eclipse. Is that a maximum or a minimum? That's going to be a maximum, right? here. Oops, and I have forgotten. This would help if we're actually looking at butane, not ethane here. This will all make much more sense. So who's this guy? This is our friend Go Share. Is that a max or a minimum? It's a minimum, right? It's not an absolute minimum, but it is a minimum, right? Okay, so these Newman projections are one type of model that we can use. That's kind of a pen and paper model. Another thing we can use models for is making predictions. Depending on the type of model that you're using. So what I want to do is make a comparison. Like I said, the two types we're looking at are physical models or computer models. I want to make a comparison of those two types, so you know why we use both types. Okay. So physical models we're not going to use in lab, but you are going to use them in workshops this week. Okay. So that's why we're going to go through this exercise of understanding both of them. It's a good idea to know why you use each set of them, okay? And then computer models are what we're going to use in lab this week. So a strength, a set of strengths for the physical models, they're tangible. You can hold them in your hand. Versus computer model, you're still going to be visualizing it just on the screen. It's easy to see in 3D. And if you get expensive ones, and these are ones like if you buy a model kit for only a certain molecule, then they are true to scale. Are mostly true to scale. Whereas strengths for the computer models are not so much these things, but you can vary what you're looking at. So you can, change a bond length, change a bond angle more easily, exchange out atoms as you're looking at things. So they're really easy to vary what you're looking at and change the compounds that you're looking at. So infinitely variable. You can measure and calculate bond angles and bond lengths really easily. And make other measurements as well. You can optimize. So with the physical models, you're stuck with the model that you have. You can't change specific lengths or specific angles. These you can optimize geometries for compounds too, and see what is the best geometry for different compounds. And you can use, so here comes our prediction too. You'll also use these to predict physical properties. Disadvantages now, it's kind of the strengths of one are the disadvantages of the other, the strengths of the other are disadvantages of the first guy. For the most part with physical models, the bond angles and lengths are averages. You're not going to be able to make them bigger or smaller. And are not usually molecule specific unless you buy the one, but then it's only for that molecule. So if you buy a model kit for organic lecture, or like the model kits you're going to use in workshop, you know, the carbon angles are all set up for single bonds to have about 109.5 angles. And the lengths are all about the same, and it's not going to give and take whether you have something really electronegative attached or not, okay? Or the angle changes slightly because a group is really large and you have some steric effects. Disadvantages for the computer models. There's tons of advantages, but unless you you know, have a really expensive printer or monitor and setup, you're still only going to be visualizing in 3D. It's still going to be flat visualization. You know, I guess if you had a 3D printer and printed what was on the screen, but that is getting into really, really expensive technology yet. So it's still only 2D visualization, even though you can make all these calculations and modify all these properties, okay? So keep these in mind for both what you do in workshop and for what you do in lab this week. There's good for both, and there's places where both cases work really well, and there's other cases where it's better to use one versus the other because of the disadvantages, okay? So some things that we need to go over for this week's lab so that you understand and everybody's on the same page as far as going through the lab. We're going to go over those, and then we'll talk about what you need to bring to lab this week, and then I'll show you how to use WebMO and have some other announcements for you. So kind of call this 4 skills, things we need to know for experiment 2. So first of all, we need to look and understand at how to read electron density maps. So in McMurray, you want to go over how to read them. Look at chapter 2 in McMurray. Look that over so you understand what the colors mean when you're looking at an electron density map. And look at examples for different compounds. In general, to go to the extremes of the electron density map, the red, what is that color going to tell you? Highest density, right? What is the blue going to tell you, the other extreme? It's going to be the lowest density, right? And then you're going to kind of follow the colors in between. The yellows and oranges are still going to be higher density. Then we get into green, and the violets then down to purple are going to be the lower densities. We also need to, besides Newman projections, we're going to look at a couple ways to represent different types of molecules. One of those is the sawhorse representation. And you may not necessarily be doing this for experiment 2 a little bit, but you also need to know it for workshop and for lecture, okay? So we want to make sure everybody's set with this. It's page 104 if you have the 6th edition. I know you guys are supposed to have the 7th edition, so most of you should have that. Page 93 in the 7th edition. Okay? And so with a sawhorse representation, instead of looking straight on carbon to carbon, we're looking at an angle with that. So let's look at butane again. What we're going to do is look at carbon 2 and carbon 3 down that bond, but we're not going to look straight on at the bond. We want to be able to see better everything around each carbon, okay? And so for this first example, I'm actually going to use ethane, and then we'll look at what butane looks like. So if we have our eclipse representation, so what it is eclipsed in the Newman projection, this is what it would look like in our sawhorse projection, okay? We're going to look down that carbon-carbon bond and actually see the actual physical bond, and then look at the substituents around each carbon, okay? So another way that you could draw this is then just in stick representation for all the carbons and hydrogens, unless you had something else attached. But that would be the same sawhorse representation, okay? Now for the eclipse, it gets a little bit trickier. We're still looking down the same bond, but we gotta fit all these hydrogens in the same angles that they occur, okay? So we're not doing anything to distort what this compound really looks like. It's just representing it in a different way so you can better see what is going on around this particular bond. And so the stick model for that is like that, okay, for the sawhorse representation. So say we did want to look at like eclipsed butane, then that would be the sawhorse representation showing all the carbons, okay? And here, you probably want to be more specific of your hydrogens versus carbons, okay? So all right. Another technique we can use for drawing is looking at wedges and dashes. And so when we're drawing, like say we're drawing methane in the plane of the board, two of the bonds would lie right in the plane, but we can't put all four, it's not a flat molecule, okay? So the way we show dimension with it is then to use dashes, hydrogen, hydrogen, hydrogen. Dashes means it's going back into the board. Wedges means it's coming back out at you, okay? So those would be the wedges and dashes that we would use for methane. Now, another tricky one that I know you guys have been working on is drawing chair conformations. And that one we're going to get a lot of practice in lab and in workshops. I believe usually it's the quiz at the end of this week. There's going to be questions on it for lecture that you're going to need to know how to draw these pretty well, okay? So just a heads up of what I know from the past. So, chair conformations. There are a series of parallel lines, and they take some practice. So practice. You use the guidelines that they're given in the textbook, and then practice going back and forth. And so you want to be able to draw chair conformations one direction and the other. You want to be able to show the chair flipping in between, okay? And so kind of this direction's chair. We want to make, so this line and this line parallel, then we want this line and this line parallel, and that line and that line parallel. We've got a little pointy here. The other thing is we want to keep in mind that the angles are still going to be the right angles. All these angles are going to be about 109 degrees for cyclohexane, okay? So then be careful in drawing the substituents. You want to make sure it's clear at each carbon using a chair conformation that your axial and equatorial substituents are clear, okay? So remember, axials are up, equatorial are more out, away from the compound, okay? And sometimes we kind of have to show a little bit of three-dimensionness here. And you don't want to make things right angles either, okay? So kind of step back and look at things once you've drawn it to make sure that it has greater than a right angle, but it shouldn't be all the way to like 120 degrees, okay? So here is chair this way. Then if we did the chair flip, then we've got to draw things the other direction. And when you flip the chair, everything that was axial becomes equatorial. Everything that was equatorial becomes axial. Okay, so you got to keep track of that. So then we're going the backwards, and usually people are, one direction is easier than the other. So here's our chair going the other direction. This guy was equatorial here. Now he's going to be the axial, and the axial is going to be the equatorial. So, same thing with the other substituents, they all flipped. And again, we had our series of parallel lines. And make sure you had to show the break in the lines to show the three dimensions for things that go across the lines of the ring. Okay, so here's the chair going the other direction. So you're gonna practice your flipping, all right? Now for lab this week, a lot of this is based off of what you are doing in lecture. So things we will need for lab this week. So instead of the pre-lab, here is your pre-lab, okay? This is what you need to do to prepare before coming to lab this week. Bring pencils with erasers, okay? You've got the answer sheets in your lab manual at the back of experiment 2 that you're going to be using for this exercise, but you may need to modify things a few times before you make it permanent in the answer sheets, okay? So make sure you bring pencils and erasers. Let's not do it all in pen. So this is the one time we're saying use a pencil in organic lab. Also, if you have a laptop, you may want to bring that. We have a computer lab reserved for each lab time. But if a couple of you will bring your laptops, or people who do have laptops bring them, then we will make sure we have computers for everybody, okay? Because the computer labs have either 15 or 16 slots, so we need a couple people to bring their laptops as well. One thing with your laptop, because as of September 1st, Chrome does not, so this is all being done through the internet. Chrome does not support Java, which is what we need to do this exercise. What you will need on your laptop is Firefox instead of Java, okay? Or potentially Internet Explorer might work as well, but Chrome will not work as an internet browser, okay? You need McMurray. You guys are pretty much the 7th edition. Bring your textbook. Bring your lab manual. That's where all the instructions are. And your answer sheets are. And then the pre-lab, nothing again in your notebook, okay? So you don't have to write anything in your notebook, but do bring loose leaf paper with you. That's probably helpful too if you want scratch paper. Review chapter 2, which we've already kind of talked about here. Look at the figures, figure 2.3, and then sections 2.3 and 2.4. You want to look at chapters 3 and 4. Specifically, structures and stereochemistry. Okay, so this is your to bring list, and then here's our pre-lab of things you need to look over in your textbook. All right, so that's all that you need for bringing to lab this week. Okay. Now, before I show you the demo, I actually wanted to go through the announcements real quick, and a couple things about melting point ranges, and then we'll show you the demo of the web and mode. Okay. Make sure thermometers. And melt temps are turned off, okay? When they're not being used. If someone's waiting for a melt temp, you can leave the thermometer on, but turn the melt temp off, or it's not going to cool down for the next person. Make sure you clean your hoods and workspace and balances and melt temp area. After you're done using that area, whether it's in your lab time or in open lab time, okay? This is a big one from last week. In my lab, there's a list of shame, drawers of shame, for people who didn't put their common equipment back in the common equipment drawer. So, common equipment goes back in the common equipment drawer. So make sure you know which is common equipment and you put it back in the common equipment drawers. Otherwise, you will be left a not so friendly pink note in your lab drawer, okay? Another reminder, friendly reminder, make sure you're not putting water in the organic waste. We've already had some layering of waste, so make sure that there isn't water in the waste. Make sure you come to lab dressed appropriately. And open lab. If you're in the lab, you need to be dressed appropriately, okay? So appropriate shoes, appropriate pants and so forth. Make sure you have your safety glasses on at all times. Otherwise, you'll be asked to leave and go change, okay? Put your samples away so we don't end up with lost samples. You all now have 2 white solids, and everybody has 2 white solids that need to be kept track of. So put your samples back in your drawer, okay? And then finally, make sure you're eating before you come to lab, either for the 7:30 lab or the 1 o'clock lab. And Phelps, I've heard, or maybe, they are supposed to be open early for cold breakfast. I've heard as early as about 7 o'clock, okay? So for the early lab people, if you have meal plan, you can still go to Phelps for cold breakfast, okay? You won't get the nice omelet and pancakes and so forth right before lab, but that'll all make you sleepy later on anyway. So, but you are able to eat, so eat before you come, okay? Questions with any of those? All right, let me, I'm gonna show you now some tricks of using WebMO, and I need someone to volunteer who has not signed in to WebMO yet either. I'm just gonna show people how to sign in. So is there anyone who wants to volunteer? Any volunteers? Okay. All right. So when you go to WebMO, you're going to use, in your lab manuals, there's instructions for how to sign on to WebMO. We're going to, this is the site we use, curry.chem.hope.edu, okay? When you go there, this is what the site looks like, and we're going to click on WebMO. We want to be in organic chemistry, okay? And then what you're going to do is you're going to use your username and password for, that is the same as your username and password for your email, okay? And you don't have to put the @hope.edu, you just have to put your username and password. So I'm going to let Matt do that, because then I need to show you how you select your section. Okay, so we're going to click login, okay? And the first time you log in, I can get them out. Oh, it's not happening. Try again. Maybe try okay, there we go. We had something funny here. Okay, so the first time you log in, you're going to use your username and password. You've got to designate which lab section you're in, so we can go back as instructors and look at your work, okay? So know which Chem 255 dash whatever you are in, okay? So like Matt's in section 4, so now we're gonna click section 4 and then log in. And then you'll be into WebMO. You only get to make that selection once. After that, you're always just gonna use your username and password to get into WebMO, okay? So make sure you make the right selection the first time. I'm going to log you out so I don't have a bunch of silly jobs in yours. Okay, thank you. Now, the nice thing about WebMO, so we used to years ago do this same exact exercise, and we had like 12 copies of it burned on the CD, and you would use the CD and do the exercise, and then you'd have to check the CD in back into the stock room, and then if you didn't finish, you had to come back and during an open lab time and use the CD again, okay? This, being that we now use it with WebMO, it is accessible anywhere you're connected to the campus server. So as long as you are logged into your computer on campus, you can connect to Curie, all right? So you can do this, you know, sitting on your bed at night, watching TV at night, however, whenever you want to do this, you know, 2 in the morning because you can't sleep, so you open WebMO, whatever you want to do. You don't have to depend on getting the CD from the organic labs, okay? So I'm going to go through and give you some tips and show you how to manipulate some of these compounds and go through some of these calculations. So as you can tell, I've done a lot of them. So one of the first compounds you're going to be looking at is you're going to look at ethane, okay? And like I said, we want to make sure we're using, I know for sure Firefox works as long as your Java is updated. And I'll show you here, there's going to be a lot of times you have to say allow and yes and go ahead with this. But as long as your Java is updated, you should be good. So you want a current version of Java. So you guys are going to use ethane for your example. I'm going to go through with propane, okay? So when we go to start a new job, now that we're signed in, we're just going to click on new job. And from the get-go, we've got to activate Java. So we'll say, okay, activate and allow now, and run. And then it'll hopefully let you do what you want to do, okay? So our build tool, this is the screen you're going to get to. All of the tools we need are along the side here, and then we're going to need a couple things from our menu up here, okay? So we'll click on our build tool, and it by default goes to using carbon. So we'll draw some carbon. So I left mouse clicked on the carbon and then held and drew a carbon by left mouse clicking, and then held on that carbon and drew another line and let go to get the carbons connected. Okay. So here we've got the backbone of propane, but we need to add our hydrogen. So if you click on the wrench, which is the comprehensive cleanup, then it'll add hydrogens in the best approximation of how they should be added. So this is kind of like the quick and dirty calculation got you this far with your propane, okay? Then you click on this arrow here, you can rotate things around, look at different parts of your compound, all right? For the first set of calculations, we're just going to look at what we can do with the different optimizations, and then we can look at some of the other more complicated calculations we can do here. So to go on to do a further calculation with our propane, we click on the arrow over here in the corner, and we're going to allow, and we're going to say okay. And then the first calculation we want to do is a tinker calculation. So this is going to be like what you're going to do for your ethane compound, which is your first compound you're going to start with when you're modeling. For the job name, I would give it a name. Otherwise, it's just going to default to naming it by the formula. So if you have to do jobs multiple times, you're just going to keep having the same job name. So I would call it propane or something like that, something to give it an actual name. For this calculation, we're looking at molecular orbitals, and we're not going to change our molecular energy, okay? So we got propane, calculation molecular energy, force field, calculations molecular energy, and force fields MM3. I'll show you orbitals here in a second. So then we click the arrow on the side, and it's thinking. If we hit refresh, probably is done. So most of these calculations do not take very long at all, okay? When you get to looking at the conformations of butane, that takes longer, all right? But most of these, it may be done faster than the WebML will actually refresh the job you've requested, okay? So then we just click on our job that we requested, and now what we wanted to see was the molecular energy, or the total potential energy. So we'll go down here, here's all the values that it calculated based on what I told it to do, and here's our potential energy, okay? And we can still rotate it around, look at it. It, you know, gave it more minimization than just the little wrench did previously. And then you can also look at different things within the compound and make different calculations. So if we select this arrow right here on the left, and we click an atom in the compound, then hold down the shift key and click other atoms that you want to make calculations for. So like if we wanted the C3, C2 bond length, by clicking on C3 and C2, then down here at the bottom, it'll tell us what that bond length is. Or if we want to look at the bond angle of the 3 carbons, I click the 3rd carbon, then we've got the bond angle calculated in the bottom here, okay? So you're gonna have to make calculations like that. For example, if we need to look at a dihedral angle, remember that involves 4 atoms. So say we want to look at the dihedral angle between one of the hydrogens on carbon 3 and then the other carbons. We select, it's really hard to see here, hang on, just make sure he is selected. Select our hydrogen here, and then hit shift. And now we've got dihedral angle there is 179.947. Okay, so basically 180 degrees between here and here. Okay. So those are the different things you're going to be looking at: bond angles, bond lengths, dihedral angles. All right. And like I said, then you will rotate things around. Okay. Another thing. Let me get a new job here. Another thing you'll use when you use tools up here is in the build menu. When we get to making our cyclohexanes, we're going to need to use the fragments. So we went build fragments. Then we need to specify its functional group. We're going to need a ring, and we're going to need cyclohexane, and usually you want the chair is what you're looking for, okay? Then you say, okay. So we're going to build starting with a chair. To get that in our screen, we just left mouse click, and now we have our chair conformation, okay? And that should be an energy minimum, right, to be existing as a chair, but we could click the wrench again, see what we get. Sure enough, we end up with a chair, okay? Now what you've got to be careful with the other ring conformations, besides the chair, if something is an energy maximum and you hit it to minimize it, it's going to minimize it to the other conformation that's lower than it in energy, okay? So for the most part, we're going to be using chair conformations, but if you use WebML for building other things, just keep that in mind. Be careful what you minimize and what you don't minimize with the chair, or with the cyclohexane conformations, okay? If we want to add things onto our compound, we can click our build tool here, and you could either add on more carbons, or if you click the periodic table looking tool, we can select what we actually wanted to add on. So say we wanted to add chlorine onto it, okay? So then we had a chlorocyclohexane, or we want to get rid of that. Oops. I'm losing my, here, we'll select it. And then if you want to get rid of the chlorine, I selected it, and then I hit backspace. Now, we have a wrench. We've got a proton back on there again, and then we could make it something else. Say we wanted to make it a methyl group. So we could just make sure that carbon is selected, and click on one of the hydrogens and now make that a carbon, and then if we hit the wrench again, then it would add all the hydrogens for that methyl group, and now we'd have methyl cyclohexane. Okay, so that's how you make attachments to the cyclohexane chairs. All right. So now let's start another new job. And now I want to show you how to find electrostatic potential. So we're going to do this. You're going to do that with ethane. We're going to do it here with chloromethane. Okay, so I've got my my carbon, and then I'm going to add chlorine onto it. Okay, and then I use the wrench. All right, so now I've got chloromethane has minimized, but I need to go on and use this arrow to do further calculations. So we'll say okay. And this time for the molecular orbital calculations, we're going to use MOPAC and say okay. And again, we should probably give it a different name. We want, for the calculation, we want to look at molecular orbitals, and then this theory, it's the way it goes about thinking about the calculation, is then going to stay at PM3. Okay, so we'll change molecular orbitals. All of this should be selected to be what it's supposed to be. Then we'll hit the arrow again. And now it's the computer cluster that it runs WebMO are now thinking. So it's this big block of computers that are doing all these calculations. Now we'll click on chloromethane and run. And then we go to the bottom where it says electron density. That's what we want to see. We'll click on the magnifying glass and we'll allow it. Oops. It's not showing it very well with color. It's misbehaving. So electron density, then let's look at electrostatic potential. There we go. Click the wrong one here. Electrostatic potential, not electron density, even though they're electron density maps. We look at what colors are present. That tells us where we've got higher or lower pockets of electron density. Now what you can do to zoom in and zoom out is, hold the wheel down of the mouse and go up and down. I'm trying to make it so you can see it all on one screen here. A little bit better. Then you can make the compound bigger or smaller. Then if you go to this icon, what we can do is actually make it so you can actually see, and this is what you're going to want to do for the problem you're doing, is change how much of the color is visible versus looking at the molecule underneath. So the opacity, you want to be able to change that so that you can see the compound underneath and what atoms are associated with the color. So as expected, our very electronegative chlorine atom is more the red area versus the hydrogens attached to the carbon are more in the blue area. Okay? And so that's how you look at electrostatic potential. The other thing with this is just make sure that you are following the directions really carefully. Okay? So now, another thing you need to know is you're going to have to be able to print screen what you're using. Okay? And so to do that, you're going to hit Alt and print screen on your computer, and that basically copies what that screen looked like, and then we can go to Word and paste it, and then we have a screenshot of what you're looking at. You're going to want to do that for the last compound, which is morphine. So you want to make sure you get it aligned in the screen so it's really easy to see everything as much as possible, and then do the screenshot and import it into Word so then you can print it out, because we're going to have you calculate the energy, but we also physically want to see it. Okay. All right. One more thing that I wanted to mention. Make sure when you're collecting melting points, we talked about it a little bit last week, but make sure that you're always collecting the range, where it first starts melting a solid and where it ends melting, okay? So you don't want the melting point, you want the range for that solid melting. Make sure with the melting points you're collecting melting point ranges.